What if everything you've ever been told about the Big Bang was wrong? Not just slightly inaccurate, but fundamentally misleading. For decades, schools have taught that the Big Bang was the beginning of everything, space, time, and matter exploding from nothing. But the truth is far stranger. Most physicists today don't even believe the Big Bang was the beginning at all. And once you understand why, your entire view of the universe will never be the same again. The Big Bang isn't just a theory about how the universe began, it's a story about how humans have tried to understand existence itself. A story filled with mistakes, revelations, and cosmic irony. What if the Bang wasn't an explosion in space, but an expansion of space? What if there was something before it, something that caused it? And what if our universe is just one chapter in a much bigger, infinite book? These questions aren't science fiction anymore. They're what modern cosmologists are debating right now. When you hear scientists say, the universe is expanding, what they really mean is that space itself is stretching, like a balloon being inflated from within. Galaxies aren't flying through space, they're being carried by it. And that realization changes everything about how we imagine the beginning. Because it means there might not have been a bang at all, only a transformation. For centuries, humans have searched for a single moment of creation, a point in time where everything began, light, matter, even time itself. But what if there was no beginning? What if the universe has always existed, shifting between cycles of birth and rebirth? Before we can answer that, we have to go back, long before Hubble, long before Einstein. Back to the time when the universe was thought to be eternal, perfect, and unmoving. Every discovery in physics began with someone asking a simple question that no one else dared to ask. And the story of the Big Bang began the same way, with people who refused to accept the universe as it seemed. The truth, as we'll see, didn't explode into existence in an instant. It unfolded slowly, like the universe itself, expanding through ideas, one revelation at a time. And to understand that journey, we need to start with the first great illusion, the static universe.
The ancient belief in a static universe. For most of human history, the universe wasn't moving, at least not in anyone's imagination. Ancient Greeks, Hindus, and Buddhists saw it as eternal, cycling endlessly, or standing still in divine balance. To them, change was something that happened on Earth, not in the heavens. Stars were fixed, eternal lights embedded in an unchanging dome. The cosmos was perfect, and perfection never moves.
When Isaac Newton published his Principia Mathematica in 1687, he gave the universe a new set of rules. Gravity became the invisible hand guiding everything, from apples to planets. But there was a problem. If gravity pulled everything together, why hadn't the universe already collapsed? Newton's solution was elegant but flawed. He assumed the universe was infinite. If there was no center, no edges, then everything would balance perfectly forever. It was a comforting vision, an eternal, symmetrical cosmos that would never change. No beginning, no end, no reason to ask where it all came from. For centuries, that was enough. Scientists and philosophers agreed, the universe simply was. But reality was waiting to prove them wrong. Because even the calmest sky hides a secret, and it begins with darkness. If the universe were infinite and filled with endless stars, then every point in the sky should glow with light. There should be no such thing as night, no blackness between stars, and yet when we look up, we see a vast, dark void sprinkled with distant fires. This simple contradiction would haunt scientists for centuries. It was called Olbers's paradox, and it was the crack that shattered the illusion of eternity. The static universe couldn't explain why darkness existed. Something had to be changing, expanding, evolving, or ending. And that realization marked the first true death of the eternal cosmos. But it would take another 2 centuries, and one brilliant mind named Albert Einstein to finally rewrite the universe from the ground up. Newton's elegant universe, infinite, balanced, eternal, had a flaw so simple that it hid in plain sight. If space truly stretched on forever, filled with an endless sea of stars, then the night sky should be brilliant with light. Every direction we looked should reveal a star. Every inch of darkness should burn with brightness, And yet when we gaze upward, we find silence, cold emptiness and pinpoints of light scattered in the void. Something about Newton's perfect infinity wasn't adding up. This mystery became known as Olber's paradox. If the universe was infinite and eternal, then light from every star that ever existed should already have reached us. But the sky was mostly black, as if something were blocking the light, or as if the stars hadn't been shining forever. Was the universe not infinite after all? Or could it be that it hadn't existed long enough for the light to arrive? For the first time, scientists began to suspect that the cosmos might have an age and a history. That single paradox broke the illusion of the eternal universe. The darkness of the night sky was not a void. It was evidence of a cosmic story still unfolding. It meant the universe might have had a beginning, a time before the stars. This realization planted the first seed of doubt in Newton's infinite model. But it would take centuries, and the birth of modern physics, to truly expose the flaw. Even though Newton's equations described gravity perfectly on Earth, they couldn't explain how the universe stayed in balance. If every mass pulled on every other, the cosmos should have collapsed under its own weight long ago. To make his system work, Newton relied on symmetry, the idea that for every pull there was a counterpull. But symmetry, in a universe that changes and moves, can't last forever. Something else had to be holding everything together. For more than 200 years, scientists lived with this contradiction. They accepted a universe that mathematically should collapse, but somehow didn't. It was as though the cosmos itself was cheating gravity, quietly defying its own rules. And then in the early 1900s, one man would come along and rewrite everything, even the concept of time itself. His name was Albert Einstein. Einstein's relativity and the smartest mistake in history. When Einstein published his theory of general relativity in 1915, the universe finally got a new foundation. Space and time were no longer separate. They were woven together into a single cosmic fabric, space-time. Mass didn't simply pull on other mass through invisible forces, it bent the fabric itself. The sun didn't drag the Earth around by force. The Earth was simply moving along a curved path in a warped space-time. Gravity wasn't a force anymore. It was geometry. This new vision of the universe was revolutionary, but it came with a problem. Einstein's equations showed that the universe couldn't remain still. If everything attracted everything else, the cosmos should either collapse or expand. But Einstein, like Newton, believed in an eternal static universe. He didn't like what his math was telling him, so he changed it. He added a mysterious term to his equations, the cosmological constant. It acted like an invisible pressure, a repulsive force pushing against gravity to keep the universe stable. This tweak balanced the equations perfectly, preserving the calm, eternal cosmos Einstein wanted. To him, it was just a mathematical adjustment, a patch to make the universe behave. But in doing so, he unknowingly hinted at one of the biggest discoveries in modern cosmology. For years, Einstein's static model held strong, even as others began to question it. He believed that the universe was timeless, unchanging, that the stars had always been there. But quietly, deep in the equations of relativity, another story was hiding. Some physicists, like Alexander Friedmann and Georges Lemaitre, took Einstein's math at face value. When they removed the cosmological constant, the equations described not a still universe, but an expanding one. Einstein refused to believe it. The idea that the entire universe could be growing, stretching, changing, it felt absurd. But the universe doesn't care what we find comfortable. A decade later, Edwin Hubble would look through his telescope and see galaxies racing away from us. And in that moment, Einstein's greatest blunder would become one of his smartest mistakes. When Einstein heard about Hubble's discovery, he reportedly said, "Then I was wrong." But in truth, he might have been more right than anyone could imagine. Because decades later, scientists would rediscover the cosmological constant and realize it might represent something very real, the energy of empty space itself. Dark energy. The invisible force that still drives the universe apart today. The discovery that expanded the universe. In the 1920s, astronomers were peering deeper into the night sky than ever before. Among them was Edwin Hubble, working with the largest telescope in the world at Mount Wilson Observatory. He was studying faint, cloudy patches of light that many thought were gas clouds within our galaxy. But one of those smudges, the Andromeda Nebula, would soon change everything we thought we knew. And with it, our understanding of the entire cosmos would be rewritten. Hubble's secret weapon was the work of another genius, Henrietta Swan Leavitt. She had discovered a way to measure the distance to certain stars, Cepheid variables, by timing their flicker. The longer their pulse, the brighter they truly were. Using Leavitt's discovery, Hubble realized that the stars in Andromeda were far too distant to belong to the Milky Way. They weren't clouds in our galaxy, they were galaxies themselves. Overnight, the universe expanded a millionfold. The Milky Way wasn't the entire cosmos, it was just one island among billions. And that revelation was only the beginning, because Hubble noticed something else, something even stranger. The light from those distant galaxies wasn't normal, it was stretched. This stretching of light is called redshift. The further away a galaxy was, the more its light was shifted toward the red end of the spectrum. And when Hubble plotted those shifts on a graph, he found a clear pattern. The farther a galaxy was, the faster it was moving away from us. The universe itself was expanding. Space was growing larger. That discovery shattered the last remnants of Einstein's static universe. The cosmos wasn't eternal or still. It was alive, dynamic, and growing. Imagine dots on the surface of a balloon. As the balloon inflates, every dot moves away from every other. That's what's happening to galaxies, not flying through space, but carried apart by it. It was the first real evidence that the universe had a beginning. But what kind of beginning? If everything was expanding, then logically in the past, everything must have been closer together. And if you wind the clock backward far enough, everything, galaxies, stars, atoms, must have once been in the same place. That idea would lead to one of the boldest theories in science. A theory proposed not by an atheist or a skeptic, but by a priest. The birth of the Big Bang idea. In 1931, a Belgian physicist and Catholic priest named Georges Lemaitre had an audacious thought. What if the universe had truly begun? Not from nothing, but from a single, ultra-dense point. He called it the primeval atom, a cosmic egg containing all of space and time before it expanded. He imagined the universe bursting outward in a brilliant, fiery event, a beginning of both matter and time. It was a vision that would later be known as the Big Bang. Lemaitre's idea was shocking. At the time, most scientists, including Einstein, rejected the notion of a cosmic beginning. They preferred the comfort of an eternal universe. Even Einstein told Lemaitre, "Your calculations are correct, but your physics is abominable." But Lemaitre persisted, convinced that the math and the data were on his side. Then came Fred Hoyle, one of Lemaitre's most vocal critics. During a BBC radio broadcast in 1949, he mocked the idea, calling it this Big Bang hypothesis. The name was meant as an insult, but it stuck. Ironically, Hoyle's mockery gave birth to one of the most famous phrases in science. The Big Bang was born, even though it wasn't really a bang at all. Lemaitre's version of the universe was not an explosion in space, it was the expansion of space itself. Every atom, every photon, every particle was once compressed in an unimaginably hot, dense state. Then, in a cosmic instant, the universe began to stretch and cool, giving birth to everything we know. The stars, the galaxies, even the laws of physics themselves, all emerged from that first expansion. But this raised another mystery. What caused the bang in the first place? For a while, the scientific community ignored Lemaitre's model. There was simply no evidence that could prove it true, or disprove it. And without evidence, the Big Bang remained a bold but unverified guess. That would change 2 decades later, when astronomers accidentally stumbled upon the universe's oldest light. And in doing so, they found the smoking gun that proved Lemaitre right all along. The hot, dense universe, the true beginning. Imagine rewinding the universe, galaxies shrinking, stars fading, atoms crushing closer and closer together. If you reverse the cosmic clock far enough, everything we know, space, time, energy, collapses into a single searing state. A universe not of stars or light, but of raw chaos, an ocean of subatomic particles colliding in fire. This wasn't an explosion in space, it was the rapid stretching of space itself. And it all began about 8 billion years ago. In those first moments, the universe was unimaginably hot, trillions of degrees. No atoms could exist. The energy was too violent for matter to form stable structures. Protons, neutrons, and electrons drifted in a dense soup, colliding and breaking apart endlessly. Light itself couldn't travel freely. It was trapped, constantly scattered by charged particles. The universe was bright but blinding, filled with light that couldn't escape. As it expanded, it began to cool. After just 1 second, the temperature dropped enough for protons and neutrons to combine. They formed the first atomic nuclei, mostly hydrogen, a little helium, and a trace of lithium. For the first 5 minutes of cosmic time, the universe was a nuclear reactor. Then, the fusion stopped. The ingredients for everything were set in stone. For hundreds of thousands of years, the universe remained a glowing fog. Matter and light still danced together, locked in a hot plasma. But expansion continued, and cooling followed. At around 380,000 years old, something extraordinary happened. The fog lifted, and the universe became transparent. For the first time, light broke free. Photons, the same ones born in that ancient fire, began to travel through space, unimpeded. That light has been traveling ever since, stretching and cooling as the universe expanded. Today, it has faded into a faint microwave glow that fills all of space. We call it the cosmic microwave background, the oldest light in existence. This light is our baby picture of the universe. When we detect it, we're literally seeing what the cosmos looked like when it was only 380,000 years old. A snapshot frozen in time, uniform, but not perfect. Tiny ripples in its brightness would later grow into galaxies, stars, and planets. The universe's earliest whispers, imprinted in light. But for decades, this light was only a theory, a prediction. Scientists knew it should exist, but no one had found it yet. And then, by accident, 2 men stumbled upon the echo of creation itself. They weren't looking for the Big Bang. They were just trying to clean static out of a radio signal, and what they found would forever silence the skeptics. The evidence that changed everything, cosmic microwave background. In 1964, 2 radio engineers, Arno Penzias and Robert Wilson, were working at Bell Labs in New Jersey. They were testing a new kind of antenna, massive, horn-shaped, and incredibly sensitive. But no matter what they did, they kept hearing a persistent background hiss. It wasn't the equipment, or interference, or even the pigeons nesting inside the antenna. The noise came from every direction, and it never went away. At the same time, a team of physicists at Princeton University, just 60 kilometers away, were searching for the very same thing. They were trying to detect the predicted afterglow of the Big Bang. When the 2 groups finally connected, the puzzle pieces fell perfectly into place. Penzias and Wilson had found it, the faint microwave radiation left over from the birth of the universe, a discovery so monumental that it earned them the Nobel Prize in Physics. That faint, uniform glow confirmed what Lemaitre had proposed decades earlier. The universe really had been hot and dense in its earliest moments, and the bang wasn't a metaphor anymore, it was a measurable fact. Everywhere you point a radio telescope, that ancient light is there, whispering the same story. It's the echo of creation, stretched across the entire sky. Later missions, COBE, WMAP, and Planck, would map this radiation in astonishing detail. They revealed slight variations, just millionths of a degree different across the sky. Those tiny fluctuations were the seeds of structure, the fingerprints of galaxies before they existed. It's like looking at the DNA of the cosmos itself. The Big Bang had left a perfect cosmic signature, but that perfection was a problem. The CMB was almost too uniform. Every patch of sky measured nearly the same temperature, 2.7 Kelvin, despite being impossibly far apart. How could regions separated by billions of light years have the same temperature? There hadn't been enough time for heat to travel between them. This puzzle became known as the horizon problem. And it wasn't the only issue. There was also the flatness problem and the monopole problem. The Big Bang explained what happened after the beginning, but not how it began. The evidence proved that the universe had expanded, but not why it had done so smoothly. The Big Bang, it turned out, was only part of the story. The discovery of the cosmic microwave background didn't end the mystery. It deepened it. If the Big Bang was real, then something had to trigger it. Something powerful enough to inflate the universe in an instant and fine-tune it to perfection. The next revolution in cosmology would reveal exactly what that something was, and it would redefine what the bang in the Big Bang actually meant. The mysteries the Big Bang couldn't explain. For decades, the Big Bang seemed untouchable, the perfect story of creation. It explained the expansion of the universe, the birth of matter, even the faint echo of radiation left behind. But as scientists looked closer, the math began to break down. There were cracks in the theory, deep ones, and those cracks threatened to unravel the entire cosmic story. The first was the horizon problem. If the universe was born in a single explosion, how could it be so uniform today? Light simply hadn't had enough time to travel between opposite sides of the sky. Those regions could never have shared information or balanced their temperatures. Yet somehow, they're almost perfectly identical, as if the universe knew how to synchronize itself. The second was the flatness problem. When scientists measured the shape of space, they found it to be astonishingly flat. Not curved like a sphere, not saddle-shaped, just perfectly, impossibly flat. The problem: flat universes are unstable. Even the tiniest deviation at the beginning would have caused the universe to collapse or fly apart long ago. Then came the monopole problem. At the extreme energies of the early universe, exotic magnetic particles, monopoles, should have formed. They'd be heavy, stable, and nearly indestructible. If they existed, the universe should be littered with them. But we've never found even one. And finally, there was the singularity, the mathematical infinity at the very start. A place where physics itself breaks down, where time and space cease to make sense. Einstein hated it. Hawking and Penrose proved it mathematically, but even they knew it couldn't be the full picture. A singularity wasn't a solution. It was a symptom, a sign that something was missing. The Big Bang Theory explained how the universe expanded, but not what made it expand in the first place. It was as if we'd arrived at the first page of a book and realized there were entire chapters missing before it. What existed before the Big Bang? What caused it to happen at all? Those questions haunted physicists. And one man would stumble upon an answer, not while studying the cosmos, but while thinking about how water freezes. Cosmic inflation, the real bang. In 1979, a young physicist named Alan Guth was trying to solve a problem in particle physics, not cosmology. He was studying phase transitions, moments when substances change state, like ice melting into water or water boiling into steam. But in his equations, Guth noticed something strange, a kind of supercooling effect that could trap energy. And that trapped energy, he realized, might have cosmic consequences. It could make space itself expand, violently, exponentially, and almost instantly. This was the birth of cosmic inflation, a theory that suggested the universe didn't start with a singularity at all. Instead, it began as a tiny region of space filled with high-energy vacuum, a quantum field under tension. Then, in less than a trillionth of a second, that field released its energy, stretching space faster than the speed of light. In that instant, the observable universe expanded by a factor of 1060. Inflation didn't just explain how the universe grew, it solved every flaw the Big Bang couldn't. The horizon problem? Solved. Everything was once close enough to equalize temperatures before being blown apart. The flatness problem? Solved. Rapid expansion flattened any initial curvature, just as stretching a balloon flattens its surface. The monopole problem? Gone. The energy of inflation diluted any heavy particles into oblivion. And the singularity? No longer needed. Inflation replaced it with a smooth, finite beginning. But inflation did more than fix problems. It made predictions. Tiny quantum fluctuations in the inflation field would have rippled through the early universe. Those ripples became density differences, seeds of galaxies, stars, and planets. And astonishingly, we can see them today, frozen as patterns in the cosmic microwave background. The structure of everything, including you, was written in those ripples. The beauty of Guth's theory was how simple it was. No divine spark, no mysterious singularity, just physics, magnified to a cosmic scale. Energy in the vacuum of space had caused the universe to inflate like a balloon, and when that inflation ended, all that energy transformed into matter, light, and the universe we know. The bang in the Big Bang wasn't an explosion. It was inflation stopping. But the strangest revelation of all was this. Inflation doesn't necessarily end everywhere at once. While it stopped here, creating our universe, it could still be continuing elsewhere, endlessly. Each bubble where inflation ends becomes its own universe, complete with its own Big Bang, its own physics, its own reality. And in that moment, the idea of a multiverse was born. The birth of the multiverse. Alan Guth's theory of inflation solved nearly every problem with the Big Bang, but it created one enormous new one. If inflation could happen once, what's stopping it from happening again and again? According to quantum physics, the inflation field doesn't decay everywhere at the same time. Some regions stop inflating and form universes, like ours. But other regions keep inflating endlessly, spawning infinite pocket universes in the process. This concept is called eternal inflation. It means that the Big Bang wasn't a unique event. It was just one bubble in an endless cosmic foam. Each bubble expands into its own universe, separated forever by regions of space still inflating. In some, physics might look exactly like ours. In others, the laws of nature could be wildly different, alien beyond comprehension. To imagine it, think of boiling water. Each bubble that forms on the surface is like a new universe, rising and breaking away. The pot, the space-time underneath, keeps boiling eternally. That's the multiverse, a cosmic sea where new universes constantly bubble into existence, and we just happen to be inside one of them. This idea wasn't born from fantasy. It emerged from equations. Quantum mechanics, general relativity, and inflation all point toward the same possibility. Our universe may not be everything, just a single branch of an infinite tree. Each universe isolated, unreachable, expanding forever in its own timeline. Infinity, multiplied by infinity. The implications are staggering. If inflation never truly ends, then somewhere out there, new universes are being born right now. Each one could contain different versions of physics, chemistry, and maybe even life. It's the ultimate cosmic recursion, a universe factory that never stops running. And it turns the question, what caused the Big Bang into which Big Bang? Many physicists resisted this idea at first. It sounded untestable, too vast, too strange. But the math kept leading back to it, like gravity pulling thought itself toward infinity. The universe, it seemed, was far bigger and far more chaotic than anyone had dared imagine. And that leads to the final question of all. What really exploded? What really exploded, and what it says about us? Here's the truth. Nothing exploded. There was no point in space where it all began. No fireball expanding into emptiness. Space itself expanded. Time itself began to flow. The Big Bang wasn't an explosion in the universe. It was the universe becoming capable of existing. Everything, all matter, energy, and even time, unfolded from a single transformation of space. So what actually banged? It wasn't matter. It wasn't energy. It was the vacuum itself, a field of pure potential energy. That vacuum inflated, then released its energy into particles, radiation, and structure. From that energy came atoms. From atoms came stars. From stars came us. We are, quite literally, the cooled remains of the universe's first breath. When you look at the night sky, you're not just seeing stars, you're seeing history. Every photon is a messenger from the past, traveling across billions of years to reach your eyes. The faint glow between galaxies, the cosmic microwave background, is the afterimage of creation itself. The universe still carries the scars of its own birth. And you, sitting here, are made of the same particles forged in that ancient fire. Most people think of the Big Bang as a story of destruction, an explosion from nothing. But in truth, it's a story of transformation. The universe didn't appear out of nowhere. It evolved from a sea of quantum energy that was already there. Before time, before matter, before meaning, there was potential. And that potential became everything. Some scientists now believe the Big Bang may not even have been the first one. If inflation continues, new universes may rise endlessly, each with its own version of physics and time. Maybe ours will fade one day, and another will bloom somewhere else. The cosmos may not have a beginning or an end, only cycles of awakening. In that sense, we are part of an eternal story, one that keeps rewriting itself forever. So what was the Big Bang, really? It was the moment when reality itself became possible. When the universe took a deep breath and said, "Let there be space." We weren't created from nothing. We were born from everything. And maybe, just maybe, that means the universe isn't just out there. It's also within us.